Control, a final project in process control and dynamics by Jim Guyman, Kimberly Harris, William Strahl, and Lohan. First, I'm going to go through the outline of our presentation. We're going to go through the background, the model formulation, the model identification, the tuning of our controller parameters, the results of our optimal control profiles, the discussion, and conclusion. So first, the problem is condensation on the windshield. When the temperature of the windshield drops below the dew point temperature of the air in the cabin, the water in the air in the cabin can condense onto the windshield, which can limit visibility and cause accidents. So we decided to implement a PID controller onto the heater of the car to keep the temperature of the windshield above the dew point so that condensation would not occur. And to do this, we looked at the physics of the system and created a model. And we created a nodal network to describe the heat transfer of the windshield. And that solves an energy balance on each node, which is a function of the conduction and convection on that node. We also implemented a heater, which is a function of time and velocity. And also the air in the cabin, we performed a mass balance and an energy balance on it in order to keep track of the temperature as well as the water content of the air so that we could accurately know the dew point temperature of the air. And this is the code. So this goes through the nodal network and this solves an energy balance on the nodal network with all the associated convection and conduction equations. This file goes through the mass balance and energy balance of the air and keeps track of the water content and temperature of the air. We have our PID controller here, and then we have a scenarios file that puts all of these together into different scenarios, like going to the grocery store or taking a trip to on the highway or going out on the freeway. And then the main file runs them all together. And the sensor is an IR sensor that's on the back of the rear view mirror, and it can sense the temperature using IR. And then the actuator is the heater, and the controller is in the CPU of the car. And so first we did model identification. We put a step input to the manipulated variable, the percent heater, and we saw that it affected the control variable or the temperature of the windshield. And here's we fit it to an FOPDT, and this is the fit. And here are parameters that we got for that fit. And in addition, we added a feed-forward controller to reject a disturbance, which is in our model, which is the velocity of the car. As the car moves, that will change the flow of the air on the outside, which changes the heat transfer. And so we also wanted to get a gain for the feed-forward controller, and so we did a step input on the heater and the disturbance, the velocity of the car, and we're able to get a gain for that. And so our initial parameters are here at the bottom. We also did a sensitivity test to see how a change in the manipulated variable would affect the temperature of the windshield. And so it's obvious that at the very beginning, having the heater on versus off makes a very big difference. But also at the end, having the heater 90% versus 100% really doesn't make that big difference. We also performed a stability analysis on our controller where we got a value of kc greater than 0 will create a stable performance for the controller. We also worked on the tuning of our controller to tune the parameters, and that included gain scheduling for the feed-forward controller. And the reason that we had to gain schedule the feed-forward controller is because the heat transfer of the windshield is a function of temperature gradient. And so the car could be moving really fast, but if the temperature of the windshield and the temperature of the outside are the same, then there's not going to be any heat transfer. So we don't want the heater to turn on the heater when there's no heat transfer. And so we implemented a gain that is a function of temperature gradient rather than a constant gain in that scenario. Our control profiles are as follows. On the left we have our initial profiles, and on the right we have our tuned. So on the top left we have our inside air temperature of the car as well as the dew point. In the middle we have the windshield temperature as well as the dew point and the set point. On the right we have the water content of the air through time. On the bottom left we have our disturbance variable, the velocity, which represents some sort of scenario like a freeway trip or a grocery store visit. And then the bottom middle shows the controller input, what the manipulated variable is doing, and then the bottom right shows the final temperature distribution of the windshield. So as you can see, the tuned controller performs much better than the initial controller. The initial controller doesn't even reach the set point the entire time over the entire time horizon, whereas in the tuned case, it reaches the set point, maintains the set point, and the increase there is from the drop in the disturbance variable. But the controller is able to handle that very nicely as it stabilizes at the end. And so our final control parameters are here at the bottom. And we implemented the controller as well on a more refined grid of 20,000 nodes, and that is the temperature distribution of that refined run. And so we put our controller in a lot of different scenarios, and it handled them very well. We had lots of different disturbance profiles, and it handled them very well. But we also decided to try to find a limited case, something where the physics would limit the scenario. And so we put a car into a warm and moist garage, and then we had it travel into a very cold environment, and this is very conducive to condensation. And we tried to maintain the set point of the temperature of the garage throughout the whole run. And as you can see, the controller did not meet the set point at all throughout the whole run, and it actually went below the dew point temperature. But the heater is 100% on. So in this case, the controller is has the heater at 100%, but still it is unable to maintain the set point, and this shows one limitation of the physics of the problem. So it shows that the controller can only do so much to combat that problem of condensation. Future work would include incorporating the heat transfer condensation into the model to more accurately show that transition from when the heat transfer happens with condensation. And so in conclusion, we developed a model for a windshield, and we implemented a PID controller on a heater in order to keep the temperature of the windshield above the dew point temperature of the air to prevent condensation.